Okay, so formal introductions afternoon, everybody on today. Not so really rainy, but overcast day. Hope those who are in flood, anybody who's flooded out, that you're all right, enjoy day home. So we're gonna continue with forces and mechanics. We're gonna cover quite a bit today. Please do note that the handouts, if they're not already in the Google Classroom, I will post them up right afterwards, okay? Now, take some notes wherever you see anything that's not written on, that's not on the screen itself. All right, let's jot down some notes. You can add it to the notes afterwards. All right, so just checking our pens. Nice and visible pens. Good, so let's move forward. We are going to go with forces. Let's get rid of you from the screen. All right, force. A basic definition for a force is a push or a pull, as we did last day. Force is the action of a mass. We can calculate force by finding the product of its mass and acceleration. Force is always measured in newtons. Please do not, when you all start doing these labs and questions and whatnot, put the units of force as kilograms. That is not right. The unit of force and weight is the Newton. All right, so just be mindful of what you all are doing when you using these. So we have our equation of force is equal to mass by acceleration. Easy equation, F is equal to ma. Types of forces. All right, we have many types of forces. It's a fundamental quantity of the universe, believe it or not. All right, so let's just see some of the forces that do exist. We have one, gravitational force. These are attractive forces that exist between bodies due to their masses. The gravitational force of a planet on an object is an object's weight. Right? So anytime we want to know what our weight is, basically the Earth pulling us down or the Earth's gravitational force on us. Right? And gravity always acts towards the surface of the planet. We have two magnetic forces. There are attractive or repulsive forces that exist between bodies due to their magnetic polarities. We know that magnets do attract and repel. We will be doing magnetism next term, so we'll look into that. 3, electrostatic forces. These are attractive or repulsive forces that exist between bodies due to the electric charge. Electrons are kept in orbit around the atomic nucleus by such forces. You all are doing chemistry, so you all understand and appreciate that we have our nucleus and we have our electrons spinning very, very quickly around our nucleus. And the only reason those electrons don't fly off into space, right? Fly off and go somewhere else is because of the attractive force due to the neutron. What lies within the neutron of an atom again? Anybody? You can put it in the chat too. What type of charge lies within the nucleus of a body, nucleus of an atom? Anyone? Remember, we have positive charges in your nucleus and particles that have no charge. So if we have positive charges in our nucleus, electrons will be attracted towards these positive charges. So it keeps them glued together. Moving on. 4, nuclear forces. These are extremely powerful attractive forces which bind together the subatomic particles of the atom's nucleus. Of almost all the forces that exist, if you're to compare them, nuclear forces have to be about the strongest of the forces that exist. Right? Even though it acts within an atom, if you were to compare it size by size, right? Nuclear forces are one of the strongest forces that does exist. 5, elastic forces. These are restoring forces produced when a body is stretched or compressed. And 6, mechanical forces. These are mechanical forces are those that exist between bodies in contact. These can be pushes, pulls, normal reaction, friction, etc. So we're going to look at, we've already covered in class gravitational force, and we're going to start looking at mechanical and elastic. We've done a little bit, even though you didn't address it as a force, but we've touched on it in Hooke's law, but we're going to see that in a little bit. Mass and weight, which we've done in class. So we're going to go through this really quickly. In regular usage, we often confuse mass with weight. We know that. We are used to saying weight when we refer to mass, and that's actually not a bad thing, but when it comes to physics terms, you have to note the difference between the two, as we did in class. In physics, these two things are very different quantities. Mass is a measure of how much substance a body has, and this value does not change readily, and it's measured in kilograms. We know that. That is the SI unit for mass is kilograms. If you do not get mass in kilograms, please note you always should be converting. Weight. Weight is a force exerted on an object as a result of gravity. Weight varies once the gravity varies, and this is measured in newtons. We did this in class, so this should be easy to get. Weight is equal to mass by the acceleration due to gravity, or simply weight is equal to mg. Weight is always a force to consider in calculations, especially when the acceleration is not given. So you're going to see when we do questions, especially when we start reaching moments, that weight is a force, right? Weight is a force, and sometimes they will only give you the mass of something. Remember, force is equal to mass by acceleration. Sometimes when we're doing questions, folks, they will not give us the acceleration, but we know weight is always acting on every single object on this planet, and that is a downward force that we can use and consider. So think about force is also equal to mg, and mg is simply the weight of the object. I'm putting up the reaction bar, the size. I will see you all. Anybody who has questions, wants to ask something, put your hand up. I will see it, or put it in chat. Okay, so we did this in class. We're not going to go through this again, where we looked at how weight changes even though mass remains the same. All right, so I think in class we looked at Mars, but here I use Jupiter because Jupiter is the second strongest body in our solar system. It's similar things. Aristotle, not Aristole. Please don't pronounce these wrong. Aristotle, right? That's how you pronounce this, Aristotle's theory. Aristotle is a renowned ancient Greek philosopher. And what he did when he was doing his research, this is way back like in BC era, more than 2,000 years ago. He was looking at how forces acted on bodies, or how motion generally moved, and how motion changed and reacted to the world around it, right? And he believed that force was a result of velocity. He was kind of right a little bit, but his thinking or his methodology was a little flawed. So let's see what he did. He taught that force was directly related to velocity, when in fact, force is directly related or proportional to acceleration. Yes, velocity and acceleration are very closely related, but there comes a point when they are actually different. So let's look and see. His arguments were based on observations rather than experiment. Okay, now this is where we have to talk about the scientific method. All right, I'm going to ask you all to read up on the scientific method very, very briefly, what it is. But basically what the scientific method is, like what we did in class, you make an observation, then you create a hypothesis, and then you set out to perform an experiment to prove whether or not this hypothesis was true. So what he did, he didn't form any hypotheses. He didn't make any experiments to check what he was saying. He just looked at how a few things were behaving, and he made a blanket statement from that. Sometimes that works, guys, and sometimes it does not. It epically fails. This is why we need the scientific method of, let's go through it again. You make an observation, you create a hypothesis, you perform an experiment that is going to prove this hypothesis, and you're going to see whether your experiment holds to be true or false. If it holds to be false, that means you need to readjust your hypothesis. All right, and you try again. Remember, we did a hypothesis with the pepper example. Same thing, right? You make a statement, you perform an experiment, and you see what you get. So this is what he looked at. Now, this is Greek philosophers, so that means he would have been in Athens, Rome. No, Athens, Greece, sorry, right? And what he looked at to pull a chariot at a greater speed required more horses, which required a greater force. Let's think about that all. That makes some sense, don't you think? Let's think about it. Sit down and really think about that, what he just said here. To pull a chariot, I'm not going to draw some horses. That's going to be, right, horses. To pull a chariot at a greater speed, you required more horses. And that made sense because if you have one horse, there's only so fast your chariot can go. If you have two horses, it probably could go faster. If you had three horses, it could probably go even faster than that. But anybody can see the fallacy or the mistake he's making with this statement. Suppose something then happened, right? Anybody can see why this is actually not an accurate statement, why it's not going to prove to be true. Think about it. Let me pause for a sec while we think. Okay, so when it came to Aristotle's first observation that he made, right? He looked at it a little correctly, but he didn't take the whole story into consideration because the weight of the chariot was now being shared by more horses. And when the weight of the chariot is being shared by more horses, obviously the weight acting or the weight that each horse had to carry would have been less. And a next ridiculous part of this, if I had a chariot, folks, when I told you it's going to hinge on the impossible, horses provided, it got faster when you added more horses. So do you think the chariot would have gotten infinitely faster? Suppose I added 100 horses. Do you think these 100 horses would have made the chariot go so fast? Something like, 100 kilometers an hour, 200 kilometers an hour, because, they said that a chariot would move at a greater speed because more horses provided a greater force. Do you think 100 horses pulling a chariot would have resulted in a chariot moving very, very fast? Let's use some common sense here.
No.
No, it's physically impossible. But this is where his theory could have broken down, either in regular sense, knowing that force acts differently, and two, you could not multiply this as in 100 horses would have never pulled this chariot at a big, big speed, which is what this law was stating. Force is directly proportional to velocity, right? Or velocity is directly proportional to the applied force. If you had a big, big force, that meant that the velocity should be increasing just as much, but there's going to come a point where that chariot could only travel so fast. Next one we have here, second law. Let's get a little bigger, sorry. Second law, a body comes to rest when the force on it is removed. Is that true? An object will stop when the force acting on it is removed?
No.
No. All right. We could think about if we roll a ball on the ground. All right. We could be pushing a ball on the ground. All right. We push the ball on the ground and we stop pushing it. Will that ball continue rolling?
Yes.
Yeah. Which is, you know, the annoying thing about playing with, you know, especially tennis balls and table tennis balls. Once they fall on and they're going to roll and continue rolling. It has nothing to do with the force that applied to it, because what he did not recognize here is that there are other forces at play. What he did not recognize is that different things act on an object that keep it moving forward and keep it from going too far. So it kind of made some sense, but he didn't think about the entire range of how objects behaved. So let's see. But Aristotle's observation way of real life situations with friction. If friction is negligible, negligible means very small or not considered, an object will accelerate when pushed along a level surface by a constant force. There is no force that results in a unique velocity for an object, and therefore Aristotle's law of motion cannot be correct. His theory was eventually discredited and replaced by the man, Sir Isaac Newton. Now, Sir Isaac Newton is the person who basically broke open the entire world of mechanics, right? Because he used proper laws, he used proper scientific method. Of course, this was, when was Newton? Newton would have been in the 1600s, I think. Was he? I will check. Yeah, 1600s. He was born in 1643. Right? And he broke open everything. And I tell you, everything basically created the world of mechanics. And my advanced students, when you all start doing calculus, he too. He came up with calculus to prove his mathematics and to prove his physics. Right, Newton laws. Sir Isaac Newton is one of the founding fathers of physics. Not only founding fathers of physics. His brilliant mind and very inquisitive mind led him to describe many aspects of mechanics and light. He was the first person to understand that white light can actually be broken up into, anybody want to tell me what it'll be broken up into? We did a question like this. We did a topic like this. What can we break up white light into?
Roy G. Biv.
Roy G. Biv, very good. Roy G. Biv will be the colors of the rainbow. He is the one that recognized and understood and did the experiments to prove that light actually made up of the colors of the rainbow. He was the one who understood why rainbows create the light that they do. All right, so let's continue reading. It is because of his work we are able to determine how to send a man into space. His work in 1643, in the 1660s to 1670, the mathematics he came up with in the 1660 to 1670 are what they required and what they used to send man to the moon in 1969. Look how long that physics and that maths was there. It's just we didn't have the technology. He invented calculus, right, which is a branch of mathematics, as a foundation of physics, engineering, and economics. As in, calculus is the basic subject, the basic topic of all of these. Right? Without calculus, we can't figure out how things change and why they change the way that they do. So continuing, we should look at 3 laws of motion that he devised. So we have our first law that we did do in class, Newton's first law: a body continues in a state of rest or uniform motion in a straight line unless acted upon by an external force, meaning something will not change its motion unless an external force acts on it. All right, just like you, if you are running, you wouldn't want to stop just like that. If you try to stop on a dime-mile running, you're going to fall over. Just like something is sitting on the table, that will not move unless something external makes it move. This law is also a statement of an object's inertia. Our definition here, inertia is described as being an object's, inertia is described as being an object's inherent laziness or its inability to change its motion. Inertia is why we wear seat belts. All right, I think I'll look for a little short YouTube video on how seat belts work, and I'll post it up with the handout. Friction is a retardant force that acts on all objects. Retardant force means it moves in the opposite direction to motion. That is what retardant force means. To retard means to go backwards or to pull back. It is a result of interactions of surfaces and molecules. Those of you all who did the homework will understand that. And I am promising you, friction will come in your next test, or if not, I will find one for the end of term exam. Promise, promise, promise. Momentum. So we're going on to a new topic now. Everything else was kind of revision. So momentum, you're going to spend today doing momentum. Next class, we'll do momentum. So momentum is the forward motion of an object due to an action of its mass. Unlike weight, objects can be propelled forward owing to their momentum. All right, so please note, mass is a scalar quantity, and momentum is therefore unaffected by the presence or absence of gravity. Let's think about this. Before we go on to the calculation, if I were out in space and somebody launched an object out in empty plain space, and it was launched at a velocity of, say, 10,000 meters per second, it is going to continue traveling at 10,000 meters per second, right? Because its mass is carrying it forward, right? It has nothing to do with weight, right? What carries something forward, moving forward in space, is its mass. All right, so here we have momentum. Momentum is the forward motion of an object. That is what we're looking at. Our general description of momentum is simply the forward motion of an object. All right, so how do we calculate momentum? Momentum is the product of mass by velocity. How simple is that equation? The symbol for momentum is common P. So common P, momentum is mass by velocity. Two simple terms to write down and to calculate. Conservation of linear momentum. You have to learn this law. That's why it's in italics. Please learn all your laws, because they do expect you to recite your laws or state your laws in exam. So the law of conservation of linear momentum states that in the absence of external forces, total momentum of a system is constant, meaning the momentum of a system, the total momentum of a system, which is mass by velocity, remains constant. So that means you can add and subtract the number as long as we don't have external forces acting. What are some of the external forces that act on a system that's going to affect this momentum? Our number one culprit is friction. But luckily at the Form 5 level, we don't consider frictional calculations. So life is nice and simple. right? Our momentum before something happens is equal to momentum after something happens, when we don't have to consider any external forces interfering with our program. So let's continue reading. The momentum of a system is the same before and after an event. What are some of these events? These events could be collisions or explosions. Collisions mean you have two objects traveling, one object and the next object. So you have one object is going to travel and hit the next one. And we have all played with marbles and balls and anything. And you all know if something hits something else, a few things can happen. If I have two marbles on the ground, I hope everybody has played with marbles. All right, or probably pool, the game pool. All right, there's so much physics in the game pool. It's not just a game that, people play to waste their time. All right, if I take two objects and roll them towards each other, let's think about two marbles. All right, I have two situations. I can roll these two marbles to hit each other. So these two marbles could be moving and they can hit each other. What are three things can happen if I have two rolling objects, like two balls rolling and then they hit each other? What are three things you think can happen regarding their motion and direction? I have two marbles. They are rolling towards each other and they hit each other. So you're now going to have this marble coming and hitting this other one, considering that both rolling towards each other. What are three things can happen when they hit each other? Anybody?
They can bounce off of each other.
They can bounce or rebound. Anything else?
They can stop.
Reading the mind, they can stop. There are actually cases, if anybody here has played like trick marbles and stuff, right? Or seen trick pool, right? It was really big professionals. They can hit a ball to hit the next one and the both of them will stop. All right, that can happen. One of them will stop or the two of them will stop. And then we have a third situation that can happen. Suppose these two objects are rolling towards each other, right? They hit, and what can happen to the two of them? All right, we have three things that can happen. They can bounce off each other, which is the most likely case, as in 99% of the cases, if two rolling objects hit each other, they will bounce off of each other. Two, they can come to a stop, a dead stop. Right? A horrible example of that is two very fast vehicles crashing into each other. Yeah, and we have two vehicles driving and hit along head on in each other. They're going to both come to a stop, depending on their energies. And three, they can stick and move off together, which we have seen if a big object runs into a car. Let's think if a truck runs into a car, that car is now going to continue moving with the truck. As horrifying as it sounds. You understand what I'm saying?
Yes.
Everybody? I have reactions.
Yeah,
I have thumbs up. Right? I have all actually. You all can use all kind of emoticons here, emojis here. All right. So remember this, we're going to go through this on the board when we go back to class. So let's see what else we have. When performing these calculations, we must take into account the sign conventions. Let's do a little bit of calculations. Let's do a little bit of questions that we can do mentally. All right, we're going to do a few exercises mentally, and then we're going to go into this conservation of momentum questions. How many questions do I have here? Oh, I have quite a few. All right, so let's just think about this. Suppose I have an object that has a mass of 2 kilograms and it has a velocity of 10 meters per second. What is its momentum going to be? You can type it out. Folks, that's a mental question. Let's pause the recording since this is an exercise. Okay, so coming back from the pause, law of conservation of linear momentum. Linear simply means to move in a straight line because we take simplest aspects of CSEC. The momentum before an event is equal to the momentum after an event. Now, this is a calculation-based topic, and we have several steps to take when we are dealing with this branch of physics. All right. First thing first, number one, the most important part, we must take into consideration our sign, or something we call a sign convention. The sign convention is simply an accepted rule across every world that does these questions and does these calculations have obeyed the sign convention. And what a sign convention means, it means if something is moving from left to right, we take the velocity as being positive. It's just simply to work out for mathematics' sake. Anything that is moving from left to right is taken, the velocity is taken as positive. And if my velocity is moving from right to left, my velocity is taken as negative. It's just simply signs for the calculation. My little tip to you, always remember, folks, when we're writing on a page, which side do we start writing on?
Left.
We start writing on the left and we move towards the right. So just remember that from left to right is the direction that we write in, and that's going to be the positive direction. All right, that's my little tip. Students can find other ways of remembering these things. So let's look at our steps, and then we're going to try a question. Number one, always allocate the correct velocity signs. Correct velocity signs meaning anything moving from left to right has a positive velocity, and anything moving from right to left will have a negative velocity. That's the very first thing when you're doing these questions. Two, we calculate the total momentum before our event. So that means we can actually multiply and add and find an answer. Three, we derive an expression for the total momentum after an event. Derive an expression means, folks, we are going to have a number and a letter. A number being a known quantity and the letter being an unknown quantity, because we want to be calculating unknown things. And then what we do, we're going to equate our before to our after and solve for an unknown quantity. All right. But the very basis of this entire topic is momentum before is equal to momentum after. So let's try an example. Let's just adjust this. I don't know why my thing moved around. All right, okay, now I have my arrows correct. So I have, let's write this down in terms of words. Let me just get this back. Entire thing shifted when I. Right, my before event, I have, let's put this into words. All right, get your pen and paper out. We're going to be working all this together, even though it's written on the screen. I have a 5 kilogram object is traveling from left to right with a speed or velocity of 10 meters per second. it is traveling from left to right, and then I have an 8 kilogram object that is now traveling from right to left at 5 meters per second. So what's going to happen when these two things hit each other? Right? Remember, we had three outcomes. We had one, they can bounce off each other, they can completely stop, or they can move together in the same direction. So what we have here, my before event, I have one object coming in from the left, I have an object coming in from the right, and when they hit each other, both of them are going to move off in the same velocity. And my after here, my 5 kilogram object is now traveling to the left with a velocity of 4 meters per second. And my 8 kilogram object is still traveling left with an unknown velocity. We want to work out what is the velocity this 8 kilogram object is now traveling with. All right, so the very first thing we do when we're doing a question like this, we write down our diagram, or we sketch a very simple diagram. Y'all, it's just circles and a line and some numbers. It's nothing complicated. Rule number 1, you allocate our signs. So you're all gonna have to help me with this one. Is my 5 kilogram object traveling with positive 10 or negative 10? Let me get back to sign convention.
Positive 10.
Right. Well, sign convention, let me write it down here. Sign convention, we move from left to right, is positive. So this is positive. Let's look here. My 8 kilogram object is traveling to the left at 5 meters per second. So is this going to be positive 5 or negative 5?
Negative 5.
Negative 5. Everybody agree with that?
Yeah, miss.
Good. Right. So for the after, my 5 kilogram object is now traveling to the left at 4 meters per second. Is this a positive 4 or negative 4?
Negative 4.
Negative 4, very good. And this one, the 8 kilogram object is still traveling in the same direction it did before. So is this V positive V or negative V?
Negative V.
Right, so we did our sign convention. That's our first thing. Very first step in these questions is to work out your signs. Now, what is our second step? Our second step is to calculate our total before. How do we work on momentum again? Let me just jot it down here. Momentum is equal to mass by velocity. So let's do our momentum before. Our momentum before is our total momentum of, everything added up each other. So it's going to be momentum is equal to mass by velocity. So it's going to be the momentum of my first object adding to the momentum of the second object. We're going to add the momentum of the two quantities. All right, so you add the momentum of the first one plus the momentum of the second. So it's going to be mass by velocity. So it's going to be 5 by 10. We're adding the next term, 8 by minus 5. So you're going to have 8 by minus 5. So you work out the individual momentums first. Folks, don't go and do this and add 5 plus 8 is 13, and then come and do some nonsense. 10 minus 5 is 5, and then you multiply the 2, and you're going to be a whole bunch of mess. Don't do that. Pretty, please don't do that. What you're doing, you are adding your individual momentums together. So we work out the momentum of the first quantity, of the first object, and we add the momentum of the second object. So 5 by 10 is 50. 8 by minus 5 is minus 40. 50 minus 40 is 10. So we have a number. We calculate numbers. 3, we derive an expression. for our after. Remember, expression means that we now have letters involved in our story. So let's dip this out. Let's get a different color. All right, so this is my first object and this is my second object. We have to find the total momentum of all our objects before and after our event. All right, so here it's going to be, this is our first momentum. So you're going to have mass by velocity. So it's going to be 5 multiplied by -4, adding to the momentum of the second object, which is 8 by -v. And when we work that out, you're going to get 5 by -4 is -20. And 8, sorry for the maxi, that's the taxi, that's very loud. 8 by -v will be -8. We cannot, so we are not going to simplify this any further because 20 cannot subtract 8v because, you know, we do not know what v is, so we cannot involve them in any kind of arithmetic. So our steps after our third one, where we derive our expression, fourth, we equate and solve. So what we're going to do, we're going to equate our before and make it equal to our after. And this is what we're going to get. We're going to get 10 is equal to -20 minus 8v. You all know if you're going to solve this, you carry the -20v across the equal sign, it's going to become +20. So 10 plus 20 is 30. The -8v remains on the side. To get rid of the 8, we divide by 8. And our answer is going to be minus 3.75 meters per second. The negative velocity indicates that the object is in fact traveling to the left. Let's go through these steps very quickly, and you all are going to try one on your own right now. All right, I'm going to put up one on the screen, and you all are going to give it a try. All right, and see if you get it. I'll leave the steps and everything up on the board. But we're going to blaze through this really quickly and see what we get. All right, so step one when you're doing linear momentum or linear conservation, 1, we allocate our signs. Left to right is positive, right to left is negative. So I have left to right is positive, right to left is negative, right to left is negative, right to left is negative. So step 1 is done. Step 2, we find our total momentum before our event. This is our before. So we find the momentum of our first object and add it to the momentum of our second object. So it's going to be 5 multiplied by -10 added to -5 multiplied by 8. So 5 by 10 add 8 by -5. So you're going to get 50 minus 40 is equal to 10. Simply enough there. That's our first one. Students usually get the first one right. All right. Second step, we derive an after expression. Remember, expression means we have an unknown. So we're going to have an algebraic term introduced into the story. So we get the momentum of our first object added to the momentum of the second object. And how do we work on momentum? It's simply mass by velocity. So it's 5 by -4 added to 8 by -v. So it's 5 by -4 added to 8 by -v. And you're going to get -20 minus 8v, leave it alone. Last point, we equate and solve. So we equate our before to our after. So before is equal to our after, and we solve for v. Everybody okay with that so far?
Yes, miss.
All right, we're going to try one. I'm going to leave this back up on the board here, but I'm going to draw the diagram, and I suggest you all draw the diagrams. All right, so again, I'm going to pause the recording while I do the drawing. All right, it's going to be simple action, or we can write it. So our before and our after. I'm going to make this one easy. Copy that down quickly. So it's going to be 10 meters per second, 10 kilograms, 15 kilograms is traveling with 6 meters per second. They will come, they will hit each other, and then they will both bounce off each other. And our 10 kilogram object is now traveling with 5 meters per second. And we want to know what is the speed the 15 kilogram object is going to bounce off. All right, so I will pause here, but we're going to work it out together. And I'm going to scroll back up to the top with the instructions. So resuming after that first question, we're going to try the second one here. We have a written question. A 5 kilogram object is traveling to the right with a velocity of 10 meters per second. It collides with a 12 kilogram object traveling to the left with a velocity of 5 meters per second. After the collision, the 5 kilogram object rebounds with a velocity of 4 meters per second. If the 12 kilogram object continues in the same direction, calculate its velocity. So my tip to you folks, draw a really simple diagram, right? All right, draw a really simple diagram of our before and after. Like before, we have a 5 kilogram object traveling to the right. So that means it's moving towards the right with 10 meters per second. And it collides with a 12 kilogram object traveling to the left. So it's now going this direction with a velocity of 5 meters per second. Look how simple that was. The English is usually the hardest thing, as always. Our after, it because our collision here is our event. So after the collision, the 5 kilogram object, so we have our 5 kilogram object, rebounds with a velocity of 4 meters per second. Rebounds means to bounce, or to bounce back, or to go back to where it came from. So that means it's going to rebound or go the other direction with a velocity of 4 meters per second. And the 12 kilogram object continues in the same direction. So it was moving from right to left before the collision. And that means it's going to continue moving from right to left before the collision. All right, everybody can see how that works, right? How you can put a simple question into a diagram. And when it's in a diagram, it usually is easier to visualize and work out. All right. So we're going to give this a try. Again, I'm sorry for those watching the recording, but you're going to give it a try. You're going to put the answer on the board. All right, afterwards. So I have before and after. What is the very first thing we do? We allocate our signs. So is it 10 positive or negative?
Positive.
Good. Is our 5 positive or negative?
Negative.
Negative.
Good. Is our 4 positive or negative?
Negative.
Negative.
And our V?
Negative.
Right. So that's step 1. Step 2, you're going to work out your individual momentums of each component and add them up together. All right. So that is step 2. So you're going to put total momentum before. We could actually do this mentally, folks, but we're starting you all up. And then our after. because here you're going to work out a total before. Our after, you're going to work out, or you're going to derive an expression for your total momentum after, which is the momentum of the 5 added to the momentum of the 12. You're going to get an expression, meaning a number and a letter equaling to a number, and you're going to solve for V. All right. All right, so those are our little points. While you're working out, I could probably do this one for the recording. So our total momentum before will be mass by velocity. 5 by 10 is 50. 12 by minus 5 is minus 60, and you're going to get minus 10. Please note a negative number never means you're wrong. A negative number simply indicates direction. Total momentum after 5 by minus 4 is minus 20. Added to 12 by minus V, you're going to get minus 12V, which is going to give you minus 20 minus 12V. We equate our before to our after. Again, next color. Orange sounds like a color. So our before is equal to our after. So you're going to get minus 10 is equal to minus 20 minus 12V. You're going to get some weird decimals in there, but that's all right. We carry our number across here. So you're going to get, when the minus 20 crosses the equal sign, it's going to become positive. So 20 minus 10 is 10, is equal to minus 12V. To get the V alone, you divide by minus 12 because you divide by a coefficient, sign and all. And V is going to be 10 over minus 12, which is, where's my calculator? Oh my, 5 over 6 is 8 point something. 8.83. All right, so we will wrap up there because we were supposed to take a little break in between, but that's all right. We are going to give these questions a try. You have 3 questions, so we're going to do this the next day that I see you all, which will be day 1. Don't know if you're doing a lab on day 1, but we'll see. All right, which should be next week, Tuesday. All right, so let's stop the recording here. Stop.